Okay, welcome. Let's get started. So let me get started with some announcements. So take a look at Canvas. You've got some assignments out there that are coming up. There's quiz 1 that is due this Friday. Take a look at the date and times due for these assignments. Homework 1 is due next Wednesday. And I think that's something like 4 p.m. I'm trying to get that turned in before class. So take a look at that. Another announcement, take a look at the Slack page. So the Slack page is up. I've already posted some kind of guidance on the quiz and I think the homework out there. So you can have discussions under the appropriate homework topics out there. And I'm going to check in every once in a while. Glad to help with that. Let's see. So also the lab kit distribution. So I'm working on the lab kit distribution, the AD2 and the electronics components. Still working that out. I will send an announcement out via probably the Canvas announcement feature. I'm working with another class to try to make this kit distribution go smoothly and following COVID guidance. So look for an announcement on that. Let's see, for clickers, I'm going to run a couple clicker questions today. I don't remember if I mentioned clicker grades. Let me say it again. Clickers count as a full homework grade. In other words, so all of the clickers will count as one homework grade. If you answer if you answer at least one question during half of the clicker days, the days we have clickers, you'll get a full homework grade. Okay, so it's not a very high bar. What else? My office hours will be right after class today, so stick around if you want to either ask questions or listen to other people's questions. That's fine too. And as always, if you have questions during lecture, chat or unmute, or shoot me the chat and remind me if I miss chats. I missed them last time. Otherwise, please stay muted to keep the background noise down. And if I drop off during the lecture for technical issues, I will get back as soon as I can. There's some thunder going on around Longmont at this point, so let's keep our fingers crossed that the power stays up. Okay, let's get started with the lecture. So you should be seeing a slide now. This is the slide deck that I started with last time. And I wanted to continue the topic of voltage. So in fact, I'm going to make sure that your screen isn't blocked. I'm going to stop my video here. So we talked about voltage, and I said it was a measure of energy transferred per unit charge when charge moves. And so we talked about this. If you have a circuit element that has 12 volts across it and charge flows, well, in either direction, you have 12 joules transferred if 1 coulomb of charge flows through X. We're going to talk a little more about that. So keep an eye. Just put this aside for now. We'll talk a little bit about this when we get to power, a lot about this when we get to power. I just want to bring this slide up to say, okay, we're going to talk about voltage now. The 2 points here that are important are that voltage has a magnitude, it has a value, and voltage is always measured between 2 points and has polarity. So let's take a look at this. Let's say that there is a circuit element X, and let me define 12 volts across that circuit element X. Let's say we've measured it, we know it. There's 12 volts with the polarity shown, and then I have 2 points A and B drawn there. So the actual polarity of the voltage is shown here. That plus, that minus, with the 12 volts in between. The plus and the minus indicate the actual polarity. There's something called a reference polarity. So let's suppose I define a voltage V1, and that voltage V1, I just make up a polarity. It's a polarity chosen. That's called a reference polarity. It's a polarity chosen for a voltage variable without actually knowing the real polarity, without knowing which side of circuit element X has a higher potential. It's okay. You don't need to know the actual polarity in order to work these problems. You can just define a reference polarity. And if you actually, I'm going to say got it wrong, it's not really getting it wrong, but your voltage will turn out to be negative. That's okay. You don't have to change your reference polarity. You just have to be consistent while you're working with that voltage. So let's suppose in this case, right, V1 and the actual polarity, the polarity of V1 and the polarity of 12 volts, they line up. The pluses and the minuses are on the same side. So V1 equals 12 volts, okay? Let's suppose that maybe I chose V1 and you had chosen V2, so some other polarity, and you call it a different voltage variable, V2. That's okay, that's perfectly fine. Your reference polarity is the opposite of mine, and it just means that your V2 will be negative 12 volts. V1 and V2 with those polarities mean the same thing, right? It's okay to have a negative voltage. There's another way of describing voltages, and that's with a double subscript notation. So much like we talked about the double subscript notation for current, this relates polarities to the voltage value. So the first subscript, this A, indicates where you should put the plus sign for the reference polarity, okay? So if I say VAB, the plus sign always goes with the first subscript, A. The minus sign always goes with the second subscript, B. So in this case, VAB would be 12 volts, given this known voltage with an actual polarity, okay? And then if I had, let's say, a variable VBA, right? VBA means, so the first subscript is where the positive side of the reference polarity goes, right, with the B on the B side, and A, the second subscript, is where the negative sign goes, right, so on the A side. So that's how this works, and in this case, VBA would be negative 12 volts. So just to reiterate, a reference polarity is just a polarity chosen for a variable. And if you're not given a polarity, you can choose either polarity. It'll work just fine. You just have to stay consistent throughout the problem, okay? So let me show you this way of representing polarity that I don't recommend. In fact, I recommend not using this notation. You'll see in your book in places there's an arrow, a curved arrow. It indicates a polarity. This looks like a current definition for a lot of people, so I wouldn't use it. In industry, everywhere else, later in the book, pluses and minuses are used. So I recommend using this polarity. And if you're forced to work a problem with the polarity up top, great, but use the polarity at the bottom. I think it's less, it's not confusing, it's unambiguous. Okay. Let's talk about types of voltages. So let's talk about AC and DC voltages and currents. Let's start with current. Suppose I have a circuit element, this blue box at the top, and I define a reference direction for that current, and I name the variable I. So if I were to plot that current I, the value of that current versus time, if it has a time varying characteristic, and if it reverses direction periodically, that current is an alternating current. It is AC. If, on the other hand, I have a constant value versus time, like this value, maybe 6 amps. So it's constant with time. It always flows in one direction, never switches directions. That's a direct current. Okay, so that's DC. DC stands for direct current. So you can apply this concept to voltages. So what are AC and DC voltages? Okay, well, let's suppose we derive or draw a box, this blue box, and it's a circuit element, and I've defined a voltage V across that box with this polarity. If I plot the voltage versus time and it looks something like this, it's time varying and it reverses polarity periodically, then that is an AC voltage, right? It's weird. It's an alternating current voltage, which seems weird. You could think of it as a voltage that is associated with an alternating current. It's just convention to call that an AC voltage.
Does AC voltage always follow a sinusoidal period?
It does not. Yeah, that's a good question. It does not. You're going to see, especially in your first and second labs, that you can create square waves, triangle waves, and so AC can be square, triangular, trapezoidal, whatever. The definition is time varying and reverses polarity periodically. Now, when you get into maybe some Fourier analysis and Fourier transforms at some point, you'll see that every periodic waveform can be represented with a sum of sinusoids. So yeah, so the answer is kind of yes, it does apply to sinusoids because every waveform can be made up of a sum of sinusoids. But I'll answer it in general. You can have a square wave. It doesn't have to be a sinusoid.
At what level of math do we get into Fourier sequences and stuff?
Yeah, right. So we're not going to get into Fourier analysis actually at all during this class. I'll mention it every once in a while in case you run into it in the future, but we're not going to get into it.
Do you know at what level we do, by chance?
Oh, I'm sorry. Yeah. So have you had Laplace transforms yet?
I think so in diff, I think.
Okay, yeah, there are ways you can solve differential equations with Laplace transforms. You'll see also in control systems, if you take a control systems course, mechanical or electrical, you'll get into Laplace transforms. And if you restrict yourself to the j omega axis, then you're in the Fourier domain. So the other kind of voltage, I'll say, is a DC voltage. It's constant with time and has a constant polarity. So if you plot voltage versus time and the value is constant, that's a DC voltage. Okay. All right, so let's do this. This is going to be the first clicker of the class. This is going to be an experiment, right? So I'm going to bring this question up. Okay, so the question is, so this is my first time using, on my end, it's called iClicker Cloud. On your end, it's called iClicker Reef, I think. And so give it a shot. Yeah, I see some responses showing up. So you have a waveform. And let me say this, there is no wrong answer to this question. Preparing you for this. It's really a thought exercise. Is this waveform AC or DC? Think about those definitions that I just showed. All right, so take about 30 more seconds. Take a guess if you haven't already. And again, clicker grades are not dependent on you getting the right answer. I just would like your participation in class. So always feel free to take a guess and see how you do. Okay, 5 seconds. Okay. So, and there will be another clicker question during this session if you missed this one, if you got to get your clicker app up and running. Okay, so here's the answer. And I kind of skipped ahead a little bit when I came to this slide. this waveform you can view as an AC component, right? So this triangular wave, this sawtooth wave, is an AC component summed with a DC component, okay? So, and this is actually pretty common to have AC and DC components in signals, especially for when you're trying to power, let's say, an amplifier over a coax cable. I'll explain that in a second. Let me get to the answer. Either answer is right. If I had to throw an answer up here, it would be both. And I promise I won't hide correct answers ever again. But I just wanted to again have this as a thought experiment, just to say, is it AC or is it DC? And think about that. For example, in a satellite receiver system, let's say your DirecTV, if you have DirecTV, there's an antenna probably on outside of your house, your apartment, and there's a coax cable, and there are no other DC wires going to it. It's just a coax cable. So actually on that coax cable between the center conductor and the braid, the shielding on it, there's a satellite signal. There's a signal, radio frequency signal coming from the satellite. Also, at the same time, there is a DC component. It powers the amplifier in that antenna. There's actually a low noise amplifier up in that antenna. And so you would see something like this. If you could put an oscilloscope that was fast enough on that coax cable, you would see an AC component, and then you would see an offset by a DC component that's actually powering that amplifier in that antenna. So signals are not, voltages are not always AC and DC. They're sometimes combined. Okay, let's talk about measuring voltages. So if you have a circuit element X and you've defined V1 with this reference polarity and you want to measure this voltage, and you have a voltmeter. Voltmeters have a plus sign and a minus sign associated with their terminals. What you do is you connect the plus sign, the plus terminal of the voltmeter to the plus side of your variable, of the reference polarity of your variable, the minus terminal to the minus side, right, of your reference polarity, and you do something like this. So if you saw 5 volts show up on the voltmeter on the screen, you would say, V1 is 5 volts. So then you could write this actual polarity 5 volts across X. Let's suppose you did that measurement and I did this. I said, well, I'm going to define my voltage V2 with the opposite reference polarity. And at this point, maybe we're dealing with the same circuit element, so there's 5 volts with the bottom polarity here. Well, I still do the same thing to measure V2. I connect the positive terminal of the voltmeter to the positive side of my reference polarity, the voltage I'm trying to measure. I connect the negative terminal to the negative side of the reference polarity of the voltage I'm trying to measure, right? So I do that, and then I would see, in this case, negative 5 volts, right? And that kind of makes sense because my polarity that I've defined, my reference polarity for V2, is the opposite of the polarity of the voltage that we measured, okay? So you would see negative 5 volts. Neither answer is wrong. Your answer is right because your V1 has the opposite polarity compared to my V2. On actual voltmeters, if you use a handheld voltmeter, you would see something like this. Voltmeters usually have multiple terminals. One is called common. That's usually the negative side. So the black lead usually goes in there. The red lead, the red test lead, would plug into, for measuring voltage, something that says V or voltage or something like that. On a benchtop meter, you'd see something like this. It's a little more complicated, but the same principle. You find the common or the low terminal on this Agilent voltmeter, multimeter. And then up here you see V, so you'd connect the red terminal to this, the red terminal to the red lead. Okay. All right. Now, so With your labs, you're going to be using the Analog Discovery 2, the AD2. So this is the header, right? This is just a set of pins to which you will plug in some wires and a connector. And you can see the labels here. You'll see this label 1+ and 1-, and then 2+ and 2-. And so these are actually two independent channels for measuring voltage. They're like two independent voltmeters. They really go to analog to digital converters. We'll talk about that later. But so you could think of 1+ and 1- as the positive and the negative for voltmeter number 1. And this is actually used as this input is used as a voltmeter and also for the oscilloscope, which you'll get to during your first couple labs. So what you do is you connect the header and you have a couple wires. You look at the quick reference sheet. I've got a video linked about that. And so the orange wire is the plus lead. The orange with a white stripe is the minus lead for channel 1. And when you bring up the software to measure channel 1, the voltage between those two leads is going to be measured. Okay. Okay, so let's talk about measuring current. Let's suppose we have circuit element X connected to wires, and the current's flowing from left to right through X, through this wire, through X, through the other wire. What you have to do to measure current with an ammeter is actually you have to break the circuit. You have to break the circuit and then insert the ammeter into that circuit. The ammeter looks like a wire. It looks like a very low resistance. We'll get to that, but it essentially replaces that section of wire. It looks like another wire, and it uses either a very low resistance to measure voltage and calculate current from Ohm's law, or it uses essentially magnetic sensing to do that. But in either case, you break the circuit, you insert the ammeter, and the ammeter measures current through itself. It measures current through itself from its plus terminal to its minus terminal. So it's going to measure current left to right through the meter as it's drawn here. So if I see 3 amps show up on the ammeter, then I know that's the current flowing left to right through the meter, and I1 would equal 3 amps. Let's suppose you did that measurement, and I happen to define my reference direction for that current going in the opposite direction. So I've defined I2. And at this point, we happen to know we have 3 amps flowing to the right through X. I do the same thing. I break the circuit, and now I have to connect the terminals of my ammeter such that it's going to be measuring current, right, from right to left. So I have to go from right to left, then into the positive terminal and out of the negative terminal. So I would do this. So if I connect the ammeter like this, right, so I have current that I'm trying to measure from right to left through X. The ammeter is connected such that that current is flowing from positive to negative terminals of the ammeter and coming out this way, right, and leaving the circuit. So this is how you would connect this ammeter, oriented with the terminal shown, to measure I2. And in this case, you can see that I2 is the opposite direction compared to this 3 amps that we measured up top. And so I2 would equal -3 amps because the arrows are in the opposite direction.
Question, Professor.
Sure.
So in this situation, I2 is like just what you assumed the current was going to go through, the way the current was moving, but then turned out to be the opposite?
Yeah, that's right. And yes, that's exactly right. So I didn't really care at this point where, I should say, I didn't care which direction positive charge was flowing. And that's often the case. You don't really ever have to get it right. You don't ever have to get the reference direction right such that the current is positive. You can work with negative currents, and all your equations will work out just fine. If the direction is specified, use it. If the direction isn't specified, you can make up your own.
Okay, thank you.
Sure. Okay. So if you look at real ammeters, this would be a handheld ammeter. Typically, you have to move the test lead over to a terminal that says milliamps or amps. And on a benchtop meter, you'd also have to move the test lead, the positive test lead, to one of the ammeter settings or terminals. Okay. Sometimes many times there are multiple terminals for measuring different ranges of current. And so you can see on this meter, this one says 10 amps, this one says 3 amps. So you don't want to exceed the rating of that terminal. You kind of have to have an idea of what you're expecting to measure. But if you do happen to exceed the maximum current when you're using a real ammeter, and if you exceed the current, the fuse will burn out and you need to replace the fuse. You won't break the meter or anything, but the fuse will blow. Okay. Okay, so let's talk about measuring current with the AD2, the analog discovery 2. Well, you cannot measure current directly using the analog discovery 2. You can measure it indirectly. The way you do it is you measure voltage and use Ohm's law. In fact, this is how many ammeters work. They use what's called a shunt, which is a low value resistance, maybe 0.01 ohms or 0.1 ohms. And then the meter actually measures voltage across that shunt and uses Ohm's law to calculate the current. So that's typical. So what we're doing here is normal. And I'll talk about that when we get to measuring current in lab. Okay, let's talk a little bit about power. I said the 3 things that we're going to work with, 3 circuit variables, are voltage, current, power. Let's talk about power. Power is the rate at which energy is transferred. So it is joules per second. It's the rate at which you're taking energy from one part of the circuit, putting it into another part of the circuit. It's measured in watts. Let's take a circuit element X, and I've defined a voltage across X with this reference polarity, and I've defined a current into X. You know, these wires extend off the page. It's connected to some other power supply or some other circuit. But I've defined I to come in from the top, go down through X, come out the bottom. And so power is the rate at which energy is delivered. And so power is equal to I times V. If I is so many coulombs per second, and V defines so many joules per coulomb, then you could see that you have so many joules per second either supplied by or absorbed by a circuit element. Okay, so the takeaway here is P equals IV. That gives you joules per second or watts. Now, there's a way to use this equation such that it will tell you if a circuit element is absorbing or supplying power. That way of using this is called the passive reference configuration. So just about every question I ask about power, calculate the power, right, on an exam, will say, use the passive reference configuration to calculate the power for circuit element X. Here's what that means. The passive reference configuration says, when you calculate P equals IV, make sure that the reference direction for I is pointing into the positive side of V, okay? And if that's not the case, you have to either flip the polarity or flip the current and write a negative sign in front of one of those. Okay, I'll show you what that means in a minute. If you do that, if you orient I into the positive side of V, then if P is greater than 0, X is absorbing power, right? It's something like a resistor, a light bulb, right? A heater, it's absorbing power. If P is less than 0, X is supplying power. It's a battery, a generator, right? Something like that. So So if you have to, let's suppose I had V with the opposite polarities. I would flip the polarities such that I is pointing into the positive side of V, and I'd write negative V there, okay? And so what? So why would you care? Why would you care? A light bulb and a resistor always absorbs power, and a generator, solar panel always supplies power. Well, think about something like a rechargeable battery. Rechargeable battery, you'd really like to know if it's charging or discharging, when it's supposed to be either charging or discharging. A rechargeable battery can either absorb or supply power. Okay. So let's try this. Let's do a clicker problem on this. Give this a shot. So you have a rechargeable battery, and let's suppose the terminals are corroded. You can't read a plus or a minus. So you take a voltmeter and you connect the voltmeter from some wires through some wires to terminals 1 and 2. And you also measure the current. And you've oriented the meters such that you're measuring VA with the reference polarity shown. You're measuring IA with the reference direction shown. And on the meter, you see VA equals 12 volts, IA equals minus 2 amps. So what is the power for that battery? What kind of energy is being transferred per unit time? And is the battery A, charging, or B, discharging?
Is the question active by chance?
Oh, yes, it is. Actually, I'm seeing responses. And if you're having problems with your clicker, maybe stick around for office hours or shoot me an email after class, and we'll try to figure out what's going on with your particular clicker reef application.
Just needed to reconnect.
Okay. Okay, so take another 10 seconds. Take a guess if you haven't already. Okay. And time. Okay, so let's take a look at this. What I like to do is draw the sort of more of a schematic view of this this battery. So I have IA in this diagram up top coming out of terminal 2. I chose to just draw that current going into terminal 1, right? So if IA goes into terminal 1 and out of terminal 2 and in that direction. So I just chose to draw it this way. VA is the voltage between terminal 1 and terminal 2 with this polarity. So I have VA drawn kind of to the left here, but remember the positive side of the battery is this terminal 1. The negative side of the reference polarity for the battery is terminal 2. So IA is actually going into the positive side, the positive reference polarity for VA. Okay, so this is actually set up to follow the passive reference configuration. So I would just multiply IA times VA, and I get negative 24 watts. Negative 24 watts means this battery is supplying power, supplying energy, so it's discharging. Okay.
So for your reference polarity, like the VA there, is that the reference or is that associated with the battery leads? I guess like yeah, never mind. Sorry.
No, that's a good question. So in this case, the VA polarity actually matches what would be written on the battery because I measured a positive voltage. But it actually doesn't matter for this as long as you, when you're calculating power, right, understanding that the positive that I have drawn here is actually associated with terminal 1, the negative is associated with terminal 2. IA is going into terminal 1, so it's going into the positive side of VA. If you line up IA, the reference direction, into the positive side of VA, multiply them together, you've followed the reference, the passive reference configuration.
Thanks.
Sure. Okay, let's try this one. So do it one more time. So here's a battery. I've got VB defined, and I have IB defined. And I've taken those measurements shown under the battery. VB is negative 11 volts, IB is 3 amps. Is the battery charging or discharging? Okay, take another 15 seconds. Take a guess if you haven't answered yet. Okay. Okay, so let's do just what we did last time. Let's draw a more schematic-like diagram where I have, let's see, VB, its positive side is at terminal 2. IB, its current, its reference direction is flowing into terminal 1. So I would claim that I actually have IB going into the negative side of the reference polarity for VB. So I have to do something. I have to either flip the direction of IB or I have to flip the polarity of VB. I chose to flip the polarity of VB. So then I just, well, flip the polarity, write a negative sign in front of VB, and then I multiply voltage times current. So voltage times current would be IB times negative VB, which would give me 33 watts positive. So that means that the battery is absorbing power, which means charging. Okay, any questions on that? Okay, how did that clicker work? Did everybody, did anyone have a catastrophic problem running through that clicker problem? And again, you can either answer now or shoot me an email later or talk after class at office hours.
Professor?
Yeah.
So it worked well. Just wondering, is there a way to see within a clicker reef if we got it right or wrong, or is that just we go over it together here in Zoom thing?
We just go over it because I actually don't have answers. This isn't. It's actually just a poll. It's not like a quiz in Reef in iClicker Cloud. So we'll talk about the answers, and then that's the only way you know is from talking about the answers.
Okay, thank you.
Sure. Okay. All right. So what I'd like to start on is talk about analysis of circuits. We're going to start out with analysis of DC circuits, specifically Kirchhoff's laws and series and parallel elements. So you've probably seen these before. I'd like to go over these as review and talk about maybe some tips that you didn't see in physics. So to talk about Kirchhoff's current law, we have to talk about the definition of a node. A node is a connection between two or more circuit elements. So in fact, it's the entire connection. It's not just the dot where two wires come together. So for example, node 1 would be that entire connection between A and B. I've just numbered these. I've just picked arbitrary numbers. Node 2 would be the entire connection between elements B, C, D, and E. So it's not just the little, it's not just a little dot right here at the junction. It's actually the whole node. You can apply KCL, Kirchhoff's current law, at the whole node. Let's focus on node 2, since it has more connections. To talk about KCL, let me define some currents. So I've defined I1, I2, I3, I4, like is shown here. I just picked directions, just arbitrarily. It doesn't matter. KCL works whether you define your variables into or out of the node. So KCL, Kirchhoff's current law, can be expressed in 3 ways, and all 3 ways mean the same thing. The sum of currents entering a node is 0. Okay, so we have to sum currents entering the node. Well, if you look at this node, we have I1 entering and I3 entering, but I2 and I4 are leaving. Well, they're not entering. So what we can do is we can flip them around. We can flip around the reference direction for I2 and call it negative I2, right? And then we can flip around the reference direction for I4 and call it negative I4. Now we have currents defined all entering this node. We can sum those currents. So I1 plus a negative I2 plus I3 plus a negative I4 equals 0. And so that is a Kirchhoff's current law equation. Okay, so the sum of currents entering a node is 0. Another equivalent way of saying this is the sum of currents leaving a node is 0. So I have I2 leaving and I4 leaving, but I1 and I3 are entering. And as you would guess, I'm going to flip around I1 to leave and call it negative I1. I'll flip around the reference direction for I3 and call it negative I3. So now I have currents defined all leaving this node. So the sum of currents leaving this node, negative I1 plus I2 plus a negative I3 plus I4 equals 0. These equations, these first 2 equations are the same. If you multiply, let's say the bottom equation, both sides by -1, you'll see that you get the top equation. So it's just an equivalent way of writing a Kirchhoff's current law equation. The third way to interpret Kirchhoff's current law is the sum of currents entering a node equals the sum of currents leaving a node. So I can just go back to my original definitions, of I1 and I3 entering, I2 and I4 leaving, right? So the sum of currents entering equals the sum of currents leaving. And you can see that's equivalent to the 2 expressions above that, okay? So that's Kirchhoff's current law. And again, you probably saw that in physics. So let's talk about Kirchhoff's other law, Kirchhoff's voltage law. To talk about Kirchhoff's voltage law, we have to define a loop. Kirchhoff's voltage law uses loops. A loop is any closed path around a circuit. Okay, so it's not a closed circuit, it's a closed path, and I'll show you what I mean. I could define loop 1 as starting here at the lower left, and I'll run my mouse, used to be a laser, around the circuit and wind up back at the starting point, and that's a closed loop. Another loop could be loop 2, where I start maybe up here at the upper right at this terminal. I go across D, I go across C, I come down, and I actually go from one terminal to another. I can jump across terminals. That's okay. It doesn't have to be a closed circuit. It just has to be a closed path that I follow to define a loop. I also don't have to pick inner loops. I can start here at the top middle. I can go across D. I can cross these open terminals, go across A, come back to the starting point. I just have to start at a point, end at the same point, and go either direction. It doesn't matter. So Kirchhoff's current law says this. It's going to give you a relationship about the sum of voltages around a loop. So to do that, let me define some voltages. So I've defined voltages across this circuit, across each circuit element with, again, arbitrary polarities. I just picked polarities. It doesn't matter as long as if you're not given polarities, you can define the polarities, and it's perfectly fine. So Kirchhoff's voltage law says this: the sum of voltages around a loop is 0. Okay, so we're going to go around a loop. Let's define a loop. Let's go to loop 1. So here is where I want to give you a tip. You could follow this tip. You don't have to follow this tip. People have different opinions on this. I like writing a KVL equation this way because I make the fewest errors doing it, right? And I think other people do too. So you pick a point on the circuit. I'm going to use my mouse. You can put your pen on your circuit, and you start tracing around the circuit. And when you encounter a circuit element, you're going to also encounter a voltage across that circuit element. And if you hit, I'll say, hit the negative side of that reference polarity for that voltage, you write a minus sign. If you hit the positive side, you write a plus sign. So you could say minus VA, right, plus VB, minus VC, back to the starting point equals 0. Okay, so let's try that again with another loop. Now notice this loop has components, circuit elements, and it also has open terminals. Now you can have a definition, you can define a voltage across open terminals. Look at like a 9-volt battery. The terminals aren't connected to anything, and you can define a voltage across it. So it's okay to have a voltage defined across open terminals. So if I start up here at the upper right where this arrow starts, I trace around the circuit, I encounter circuit element D. It has a positive sign for VD, so I say plus VD. And then I come down here and I hit element C. I'd say minus VC. And then I come over here, I've encountered VX. I say minus VX because I hit the minus sign. Now I'm back to the beginning. So that lets me write this equation, right? It's dirt simple. I think it reduces errors. Let's do loop 3. So if I start here at the top, okay, I trace around minus VD plus VX minus VA plus VB equals 0. Don't forget the equals 0, right? So I've written a KVL around that outer loop. Okay. So there are some who might want to say, well, wait a minute, if I, let's say, go across element A, starting at the bottom, going to the top, I'm actually going from VA's perspective, a lower potential to a higher potential if VA is positive. So why don't I write a plus, because I'm going up in potential as I cross it? And I'd say, yeah, you can do that. Where it gets confusing, though, is if VA is a negative value. Let's say it's -6. So you come here, you hit the negative sign, and you say VA is -6, so I'm going from negative to positive, so I'm going up in potential. But wait, the voltage is negative, so I'm going up potential by a negative value, so that's going down in potential. But wait a minute, I'm going up by so you can confuse yourself. That's my point. I like to say, if you hit a negative, write a negative. If you hit a positive, write a positive. And then write whatever number is here. So if VA were -6, I would run my mouse along, I'd say minus -6. If VB is -2, I'd say plus -2. If VC is 5, I'd say -5, right? So I think it makes it easier.
Question.
Yes.
When following a loop, do we have to start from a positive terminal to emulate the flow of current, since current is the flow of positive charge?
You do not. You can go either direction and start anywhere. Right. Yes. So you don't have to choose a direction based on whatever polarities you know in the circuit. You can go either direction. Okay. All right. So let's see. It is 6:10 at this point, and so what I'd like to do is end class right here. So let's do this. So thanks for joining class again. I think it's really good to join the live class so you can ask questions and hear other questions or ask questions based on other people's questions. So thanks for joining the live class. I hope it's working out well. If you have a problem hearing me or seeing anything I'm showing on the screen, or there's any other thing you need, let me know. Check out the assignments on Canvas. Check out the schedule for those assignments on Canvas. There are a couple coming up that are due. Also, see the Slack invitation link if you haven't joined Slack yet. And if you have, check out the workspace. I've already put some information out there about getting started on the quiz and I think the homework. And then also look for an announcement on the lab kits. I'm working that hard trying to get an answer there, and we will get the lab kits to you in time for your lab so that you won't have to rush. Don't worry about schedule. We'll get that to you. So what I'll do is I'll start office hours in about 2 minutes. And what I'm going to do is just go muted for a second. I'll keep the Zoom session up. If you'd like to join and ask questions or listen to other people's questions and not ask questions, that's fine too. And if you don't join office hours, I will see you next time. Again, thanks for joining the live class.